Hello friends. So during our discussion we were able to look into the approximation of integration. Now similar to the differentiation, this approximation also stems from rather the first principle description of what an integration is. So if you consider a function, any function, and if it can be illustrated in this manner, and if you want to integrate this function between two limits, a lower limit a and an upper limit b, now this integration of this function f of x is nothing but the area that is rather enclosed by this curve between the limits a and b. So from this geometrical understanding of what an integration is, that is the area that is enclosed by the curve within the limits a and b, the integration can be approximated by considering separate or partitioning this region that is enclosed by a and b into definite rectangles. So these are rectangles, and then summing it all up. So when you consider all these individual rectangles, and we can sum it all up, and this can be achieved. So when you express the sum of all the area of these individual rectangles, they yield us a summation expression which is referred to as the Riemann's expression. And this Riemann sum is what we use to approximate the integration, and therefore this sort of an integration approximation is what we refer to as the Riemann's approximation. Now when you want to write it numerically, what essentially we are doing is, when we are considering these, or when we are partitioning the area under the curve within the limits a and b, what essentially we are doing is we are introducing additional points along the x-axis between a and b. So these set of points can be referred to as, or they can be written as x1 or x0 to start with, x1, x2, so on and so forth till xn. The initial starting point that we have, that is x0, it corresponds to the lower limit, and the final point, it corresponds to the upper limit. Now when you want to rather estimate the area of this individual rectangles, then there are two possibilities, for particularly when you want to estimate the length of this rectangle. So particularly the length of this rectangle, let me highlight it in red. So when you want to estimate the length of this rectangle, so there are two possibilities. Either you can consider the value that is at a or x0, or you can consider the value at x1. So you can consider either x0 or you can consider either x1. So there is a scheme called as midpoint approximation, where in addition to these set of points, we also consider additional set of points which are the midpoints between x0 and x1, x1 and x2. So therefore these are considered, these are separate set of points, and these indicate the midpoints between these points that we have already introduced to partition the area under the curve into rectangles. So when you introduce these midpoints, so xn minus 1 midpoint, when you introduce these midpoints, what it enables us to do is, it enables us to approximate the length of these individual rectangles as f of x0 star, or in a more generalized way, we can express the length of these individual rectangles as f of I naught star. Now the width of these rectangles are nothing but the difference between these 2 points that we have already introduced to separate the area under the curve into rectangles. So the width of these individual rectangles are x of I minus x of I minus 1. So this is the width of the rectangle. So ultimately, when you want to sum this up, so when you want to sum up, or when you want to estimate the area that is enclosed by the curve within the limits, then it can be written as summation of I, that is moving from 1 to n, and f of I star, that is the midpoint, and when you involve star, it is the midpoint, and from the midpoint we are estimating the height of the rectangle and the width of the rectangle, which is expressed as xi minus. Now it is possible for us to rather make a common mistake that this I, assuming that the I ranges from 0 to n, but even though the I ranges from 0 to n, in this summation, if we introduce I as 0, we will then introduce an unknown point, the point that is not considered within the limits, that is I 0 minus 1. So So therefore we have to be very much careful when we are introducing the appropriate limits for the summation. So I, even though when you consider a set of point, it begins with 0. In this case, for the summation, it should begin with 1. Only then we will be considering the points that are rather enclosed within the limit. If we substitute I as 0, we will be moving away from the limit, because here in this term will then turn into x minus 1, or the x of minus 1. Now, so this is what we refer to as the Riemann sum. And when this Riemann sum, or in this case, it is also possible for us to rather make some simplification. That is, when the space between these points are constant, then it can be referred to as the delta x. So then what essentially we are doing is we are rather replacing the summation term with delta x. So but we have to consider this delta x for n different rectangles. So therefore we need to add an n to it. So the whole expression then can be written as this Riemann sum can be written as n delta x summation of the different lengths that vary with the midpoint. And now between a and b, the delta x can be also written as the delta x can also be written as b minus a by n. So when you substitute this, then the Riemann sum, it's a Riemann sum, it translates to b minus a of I ranging from 1 to n f of xi star. So this is the generalized expression of the Riemann sum. This is rather a simplified version of it, wherein we have made this assumption that the spacings between the different points that enable us to rather discretize this entire region into different rectangles are constant. And as you make that assumption, we end up with this expression here. Now the Riemann sum, it translates into Riemann's integral when we introduce the limit, that is n tends to infinity. So when we introduce this limit, this Riemann sum will translates into the integration, which can now be written as another lower limit is a b f of x dx. So this is rather the Riemann's approximation or the Riemann's integral of to find the integration or to integrate a function between the limits a and b. So this stems from the Riemann sum. Now towards the end of the previous discussion, we saw that the Sivra suggested that it is possible for us to, instead of discretizing or instead of partitioning this region here. So again, when we have a function and instead of partitioning this region into rectangles with constant or the equal lengths and equal widths, it is also possible for us, supposing if you have a function like this, instead of partitioning these boundaries or these limits, the area within these limits a and b into rectangles, it is also possible for us to discretize it into trapezoids. Meaning the reason why this trapezoid comes into picture is because when you discretize this area into rectangle. So for the sake of discussion, let us consider a rectangle of this sort. So this is your x1 point and this is your x0. So if you consider the first rectangle, this would be your approximation for that we have considered for the Riemann sum or the midpoint scheme of the Riemann sum. Now it is also possible, if you look closely, it is also possible if we consider a trapezoid in the place of this rectangle, we will be able to reduce the deviation between the approximation that we are making and the actual curve. So when you consider the rectangle alone, you have an error of this much. So there is this amount of error when you consider just the rectangle and the curve. However, when you replace this rectangle with a trapezoid, so when you replace it with trapezoid, what you will end up having is you will end up reducing. Of course, there will be an error. If you zoom in, you will be able to see some error, but the error will be considerably reduced when you replace the rectangle with the trapezoid. So in that case, the approximation scheme, the way we write the approximation will be very different because we are replacing the fundamental discretized shape from with trapezoid. Initially it was rectangle, now we are replacing it with trapezoid. So correspondingly, the approximation expression will also vary. So when we write down this approximation expression, still we are discretizing, we are introducing several points between a and b. So therefore still we have the set of points. However, now the shape of this this different partitioning that we are making is now changed from rectangle to that of trapezoid. So therefore we need to consider the area of this trapezoid. So the area of this trapezoid then would be, so the width of the trapezoid itself is going to remain the same, so therefore it will be x of I minus x of I minus 1. However, now that we are considering trapezoid and they have a significant difference in the length, so this significant difference in the length is expressed as 1/2 of f of I plus f of I minus 1. So we are considering 2 points, x0 and x1, and we are considering the area between this trapezoid, the area between the trapezoid that is highlighted in green, that is rather demarcated by the points x1 and x0, and this area of this trapezoid can be represented in this manner. So this is the generalized expression for it. And when your I, it ranges from 1 to n, you will be able to approximate the area that is enclosed between the limits a and b using these different trapezoids, and these different trapezoids are rather the points or the coordinates of these different trapezoids are being captured by these different points here, xi, xi minus 1, the corresponding values when you introduce these xi and xi minus 1 into the function that depicts this curve. Now, of course, this is the generalized expression. Now, it is also possible for us to expand this expression, meaning when you consider, when you substitute this I and when you expand this expression, what you would end up having is, when you consider the sum of individual trapezoids, what you would end up having is x1 minus x0 plus f of x1 x0, and when you consider the second trapezoid, it will be 1 by 2 x2 minus x1, and the product of f of x2 and f of x1, and so on and so forth. We will have f of x n minus 1, or rather xn minus 1, then f of xn plus f of xn minus 1. So what essentially we have done is we have expanded this generalized expression. The reason we need to do it is because these terms, that is x1, it gets repeated, and the same way the x2 gets repeated, except for the initial and the final point. Except for the functions of the initial and the final point, all the other terms, they get repeated, meaning the function of x1, the function of all the other points, x1, x2, x3, and so on and so forth till xn minus 1, all these points get repeated except for the first, that is function of x0 and the function of xn. Now in that case, then what happens is there will be these functions of these points, the functions of x1, x2, and so on and so forth. They have a specific, they would then gather a coefficient 2, and the rest will remain the same. x1, x2, x3, so forth, twice f of xn minus 1 and f of xn. So in addition to this, we have the difference between the points that we are considering, that is x1 minus x0, x2 minus x1, xn minus xn minus 1. So these are the difference between the points that we are considering. So if we assume that these points are equally spaced, then we can take this all out and we can replace it by delta x. And even though all the points that lie between a and b, they have gathered a coefficient of 2, there are these initial and the final points which have not yet gathered any coefficients. So therefore, they will be of this form, f of x0 and f of xn. So now ultimately what then we have is the sum of all these trapezoids that we have included to approximate the area that is enclosed by point A and B is written as delta x by 2 and the sum of this different terms here. And this will help us approximate what is the area under the curve within this upper and the lower limit. Now again, when the n tends to infinity, what essentially then we would have is we would have this we would have then approximated the integration between a and b for the function f of x dx. So this is how the expression, the approximation scheme for the when we use and when we replace the rectangle with sub trapezoid looks like. Now Again, when you consider the error associated with these, both the trapezoid and the Riemann sum, the Riemann integration, what essentially we observe is the error it stems from, when you consider the error that we have notified here, when we that we have indicated here, that when we are replacing actual curve, when we are moving away, when we are deviating from the actual curve by introducing a shape that would be possible for us to handle, what essentially we are doing is we are introducing an error, and this error depends on how this curve is varying with respect to this particular axis, or in this space here, how this curve is varying. Depending on that, your error would vary. If your curve is, if it behaves like a straight line, then it would completely overlap with the trapezoid. If it is a constant, if it's completely an horizontal line, it will overlap with the rectangle. Now, depending on how this curve varies in the space that we have considered, so in the space that we have considered, depending on it, the error that is associated with the approximation would vary. So therefore, our approximation error, be it in the midpoint or in the trapezoid scheme, it is directly proportional. When you consider what are the factors that contribute to the errors in this integration approximation, so one of the factors that largely contributes to the error is how the nature of the curve, what is the nature of the curve, or how the curve is varying in the space that we have considered with respect to the x-axis, how the curve is varying. Now, when you consider the variation of this curve, a definite way of quantifying it would be considering the second derivative of this curve with respect to x-axis, because if you could recollect during our initial discussion of the second order ODEs, we saw that the second order, what it essentially tells us about is how the variation of a function is, what is the rate of the variation of the function is. So when you consider that in the context of this curve here, what second derivative tells us is what is the curvature of this curve here. So therefore, when we say the error of the approximation depends on how the particular curve behaves in a given space, the curvature of the curve captures this behavior. So therefore, the error is proportional to the curvature of this particular plot, the particular curve that we are considering, and the curvature of it can be determined by considering the second derivative of this function. So therefore, the error is directly proportional. The error associated with the integration approximation is directly proportional to the curvature of the curve at a given point. And in addition to that, we have imposed this limit. That is, this limit ensures that, or this limits, it translate our summation to that of the integration. When the limit, when this n, when it tends to infinity, then we are essentially getting closer, the summation is getting closer to the integration. The reason is because when your summation is when your n tends to infinity, then what essentially it means is that the number of partitioning that you are doing is subsequently increasing. The area that you are considering through this approximated shapes, that is, be it trapezoid or be it rectangle, the number of such partitioning that you are making, the number of discretization that you are doing, the discretization that you are doing, this will correspondingly increase when your n tends to infinity. So therefore, when you keep on increasing your n, of course, that will occur at the cost of your computational resources. Despite that, if you keep on increasing your n, essentially what then you are achieving is you are getting closer and closer to the area that is rather enclosed by this curve. So therefore, as n increases, as n tends to get near to the infinity, or as n tends to infinity rather, in those cases the error associated with the approximation decreases. So while the curvature of the function, it increases the error is inversely proportional to the number of partitioning that we are considering, the number of points that enables us to partition the given area. As it increases, the error correspondingly decreases. Now, when you consider this curvature, of course this curvature is going to vary with the points that we are considering. So therefore, the number of points that we need to consider, it lies between the upper and the lower limit. So therefore, this is rather scaled between the upper and the lower limit. So ultimately, when you consider the factors that dictate the error of the integration approximation, there are two components to it. One is the curvature of the function, and the other is the number of points that we are taking to rather discretize or to rather partition the given area. And now when you increase the partition, the number of partition you are doing, then correspondingly your error will decrease. However, when the curvature of the given function is randomly varying, or it's quite varying a lot, then in that case the error associated with the approximation will increase. And this variation, it also will change with respect to the upper and the lower limits that we are considering. So between the upper and the lower limits there are several points, and as the upper and the lower limit increases, the corresponding points will increase. Therefore the curvature associated with this point, that is the possibility of it getting scaled. So therefore we include this prefactor, this constant, along with the influence of the curvature. So while the curvature, it influences directly the error associated with the approximation, the number of partitions that we make, it inversely influences the error associated with a given approximation function. And actually it's just not n, it's in the range or with the order of n square. And instead of getting into the derivation aspect, so this is how we will just consider, or we will just observe that how the error is being related to the number of partitions that we make, and if it affects the error. So this particular term, it affects the error, or the number of partitions that we make, it affects the error by the order of n square. Now when you consider all these together, when you sum up all these different factors that contribute to the error of the function together, then ultimately, and you replace this with c, that is the curvature, then the expression that quantifies the error will be of this form here. So instead of deriving this expression, what we have essentially done is we have considered how the curvature influence quantitatively, or we have gained a conceptual understanding of how the curvature influences the error, and what is the reason we have introduced this b minus a constant. B minus a is the difference between upper and the lower limit, so it's a constant, and how the n, or what is the relevance between the n and the error associated with the approximation that we are making. Now with this we would wind up considering that like in our previous discussion we saw that when you consider the relevance of the integration with respect to that of the differentiation, particularly when you are considering or when you want to model a temporally evolving system, owing to rather a relatively less dominant role played by the integration, we have spent correspondingly less amount of time in approximating or in dealing with how ways to approximate the integration. So with this we will wind up our discussion on the integration, and we will move on to looking into few fundamental concepts that has to do with the vector. So in this lecture what we will be doing is we will be revisiting the concept just to brush up a fundamental understanding of vectors. So vector, the definition that we learned from our in the school days itself, so it comprises of two components. One is the magnitude and the other is the direction. So the way we generally write a vector is with a arrowhead at the top, and we write, so when you expand this given vector, the way we would do it is in this manner. So what essentially we have is a vector that comprises of these values, which we often refer to as the magnitude, but these are just numbers, so they are scalars, and we have specific directions, so we have specific parameters that indicate the direction along which this vector is oriented. Now when you consider these directions, they are generally perpendicular to each other. So often, except for a unique application, generally in the context or particularly in materials research, except for few specific applications, we generally consider these vectors to be perpendicular to one another. And this is how we rather graphically represent these directions, that is I vector, k vector and j vector. Now these vectors, they form a basis using which we are able to represent this a given vector. These set of vectors, vectors I, j and k, these indicate a specific direction. And one other key component of it is that these vectors, they do not have any magnitude of their own, so their magnitude is 1. So these are referred to as the unit vectors, and these unit vectors, when augmented with the appropriate scalar, appropriate magnitude, they help us define a specific vectors. So these are unit vectors, they are oriented in perpendicular direction, and these form the basis of describing any given vector. And when you consider this, they appear similar to that of the coordinate system, and these coordinate system often we refer to, because when they are perpendicular, we refer to this as, so if you consider this as your z-axis, this as your x-axis, and this as your y-axis. So what essentially we have is these vectors that we have considered, these bases, they form, or they appear to form a part of this coordinate system, and this coordinate system we often refer to as the orthogonal coordinate system. And similarly, the reason we use this term orthogonal is because they are perpendicular to each other in a given space. They are perpendicular to each other, so therefore we refer to them as the orthogonal coordinate system. And since these vectors, they form a part of this coordinate system, and they are perpendicular to each other, the term ortho remains the same. However, these are referred to as orthonormal bases, not orthogonal basis but orthonormal basis, because when you differentiate, or when you say that these I, j, k are the basis of our vectors, what you are implicitly assuming is that in addition to the direction, the magnitude of these vectors are equal to 1. So therefore, we need to ensure that while we are describing it, the unit vectors, or these magnitude 1 of these vectors, are being explicitly made clear. So therefore, the normal term here ensures that the bases that we are considering are of unit value. So therefore, we refer to these bases as orthonormal bases. So orthogonal coordinate system does not ensure, the orthogonal basis does not ensure that the vectors that you are considering to, or the unit vectors that you are considering to rather represent a given vector are of unit length. So only when you state it is an orthonormal basis, we will be able to understand that these vectors are of unit length. These vectors that are perpendicular to each other are of unit length. Now, when you consider two vectors in addition to A vectors, if you consider another vector of using the similar notation, when you represent another vector using the similar notation, the sum of these two vectors is rather straightforward. All we need to do is sum the magnitudes that are associated with these given bases. So we need to sum these two, that is AI plus BI and AJ plus BJ, and finally AK and BK. So when you sum these two different of the magnitudes that are associated with a given orthonormal basis, then we end up summing these two vectors of A and B. So we have A and so I vector plus J vector K vector. Now when you consider graphically or geometrically what the summation means, so you have your basis. Let us say that, so instead of considering just the basis, let us consider the orthogonal space. So when you have your orthonormal basis, from the orthonormal basis we can consider based on this orthonormal basis, let me repeat, so we have your I vector, J vector and K vector based on this orthonormal basis. Again, since these bases are perpendicular to each other and they are similar to the coordinate system that we use to describe the space, the actual space. When we want to describe the actual space, we need a coordinate system, and since these orthonormal bases, they can be superimposed and they lie over this coordinate system, this space that is created by these unit vectors, they can be referred to as the vector space. So this is one of the key components or one of the terms that we need to get familiar with, because even though our real space is confined to three-dimensional system, it is possible for us to conceive a multidimensional vector space. Let me repeat, we have I, j, k vectors and these are mutually perpendicular to each other, and this orthonormal nature of this unit vector is similar to the orthogonal nature of the coordinate system that we use to describe our three-dimensional world. Now, therefore, it is possible for us to treat the space of the coordinate system that is created by the ijk vector as a vector space. Now the reason we just consider ijk is because the space that we are able to possibly conceive, the highest dimension that we are able to possibly conceive is rather 3 dimension. However, it is also possible for us in the space, when you consider move away from the actual space, the actual dimension to the vector space. Now the vector space is now defined by ijk vector. Now when you move into the vector space, it is possible for us to consider more than 3 dimension. So it is possible to have a multi-dimensional space vector which is greater than 3. Now that is possible because we have started our discussion. The reason we are able to relate these vector coordinate system or these vectors, the unit vectors, the coordinate system that is created by this unit vectors as the space is because it is something similar to what the coordinate system that is x, y, z will render us. Now when you consider in such a vector space 2 vectors a and b, say for instance a vector a and vector b, the sum of these 2 vectors can be rather ascertained by placing this vector here, that is a vector here, and dropping a diagonal from here to here. So this is what the sum of the vectors means. So geometrically this is what the sum of the vectors means. It is also possible for us to rather drop or consider the b vector here. So these are parallel. We can consider the b vector here and then join the initial point to that of this point here, and you will be able to achieve geometrically represent the sum of a and b. Now when you consider the difference of the vectors, so what essentially the sum of a and b vector is that we have different components for that is associated with a given orthonormal basis. For a given orthonormal basis, when you consider 2 vectors, there are specific components associated with it. In case of the ith basis, we have 2 components. So what essentially we are doing is we are augmenting both. We are summing up these both magnitude along the same directions. So along the same directions, 2 vectors gives us 2 different magnitudes, and when we are summing up, we are rather rubbing these 2 up in the same direction. And when we do that, ultimately a graphical representation, the sum that we get will be of this form, and this is how we can graphically represent it. Now when you adapt the same understanding to the difference between 2 vectors, what we have is we have the representation of each of these vectors. We have definite components that are associated with definite scalar components that are associated with each of the individual orthonormal bases, and in case of sum, we added up these components along a given orthonormal basis. Here we are just removing a part of this magnitude in a given direction. So initially what we did, we added we have a specific scalar along as ith or j or k basis, and we added to that a specific value, a specific scalar value, and that is how we ended up with this expression for the summation of the vector. In case of the difference of 2 vectors, we are removing some of the magnitude that is associated with a given basis, and that is essentially what the difference between 2 vectors mean. And when you consider the geometrical representation of it, again you have 2 vectors. Here a vector and your b vector. The difference a minus b will be this. The difference a vector minus b vector will be this. Now the reason again why we have this particular direction is because when you consider this particular direction, the reason we have this direction is because we will be able to see that when you sum up these 2, that is a vector minus b vector with that of the b vector, when you sum these 2 up, it is possible for us to observe that we go back to our a vector. Let me repeat, this is the graphical representation of the difference. The difference is nothing but we are removing the magnitude associated with a given basis with respect to another vector. So we have 2 vectors, we are taking the difference, and what essentially we are doing is we are removing the magnitude. We are rather taking some part of the magnitude of a vector that is associated with a given basis, and that's the reason we are able to graphically represent it in this manner. The reason why we are sure about this particular representation, this particular direction of a minus b vector is that when you consider the summation of a minus b vector and b vector, so we know how to graphically consider the summation of these 2 vectors. So a minus b vector can also be expressed as this. So this would be A minus B vector. So A vector minus B vector. And now what essentially we are doing is we are projecting it here, or we are taking or tagging it here. So instead of considering the summation here and here, we are tagging it here like we have done during the summation, or while discussing summation, we took the A vector from this spot and we have placed it here, and then we were able to draw the diagonal. So the same here, this A vector minus B vector could be here. So we took this from this position and we moved along from this position, we have placed it along here, and now when you sum these two up, these two get cancelled out, and ultimately what we are left with is A vector, and now the A vector is projecting along the direction that it should project had we started off with A minus B vector plus B vector. So that is how we end up with this graphical representation and with this particular direction here. So what essentially we have now considered is what is the significance of the sum of the two vectors and how we can graphically represent it, and what is the significance or what is the meaning of the difference between two vectors and how it can be graphically represented. Now when you consider going back to the vector space that we have considered, the reason we were able to restrict ourselves, or so far what we have been considering, is rather a three-dimensional vector space. So it's a 3D vector space is what we have been considering. So the reason we have been restricting ourselves to the 3D vector space is because it helps us translate our basis to a coordinate system. Now when you consider, or rather a most relevant example for a multidimensional vector space would be the composition that we consider for a given material. Now when you consider a given material that is being used in an application, of course all this needs again to get tied up with the materials research or our principal domain. So therefore when you consider the composition of a material that is used in an application, be it an alloy that is used in an application, very rarely the composition, the alloy composition that we use would be of one base metal and just two alloying elements. Very rarely you would observe such an alloy being used in an application. Often what we have is we have an alloy that comprises of more than 3 or 4 alloying elements. So supposing if you are doing a tensile testing for a given sample, and if you want to measure the composition of the sample, you send it elsewhere and you measure the composition of the sample, you will notice that this particular sample comprises of a wide range of alloying elements, and correspondingly the property of the material will vary. So when you consider the different factors that contribute to the contribution, or the concentration of different alloying elements that contribute to the overall composition of the material, it is more than 3 materials or 3 alloying elements often. So it will be often greater than 3 alloying elements. When you consider the composition will often be greater than 3 alloying elements. Now when you want to represent the position of a composition in a space, so you want to represent the position of this given composition in a space, and now this space comprises of more than 3 alloying elements. Then in that case what you would need to do is you would need to move away from this 3-dimensional vector space to a multi-dimensional vector space. So let me repeat, if you have say a ternary alloy that comprises of iron, example manganese and carbon. Now when you want to represent a given concentration, or when you want to graphically illustrate a given composition of an alloy, of a ternary alloy of this sort, since we have already seen that it is possible through appropriate description of the composition to treat this as a dependent variable, and there will be only 2 independent variables. So you can consider Mn and you can consider C, and therefore a point here would represent the composition of one of the ternary alloy. Now in addition to manganese, suppose you are introducing chromium. So earlier your ternary alloy, it comprises of 2 alloying elements, now it comprises of 3 alloying elements. Now in order to ensure that you are accurately capturing your concentration, you are accurately representing your concentration, then you need to introduce a 3rd dimension that will give you the range of chromium that is present in your alloying element. And then using this three-dimensional space, you will be able to represent a composition. You will be able to represent the composition of an alloy that comprises of three different alloying elements. Now supposing in addition to chromium you are including molybdenum. Of course these are not theoretical, these are actual alloys that we use. Actual are stainless steel, so this could be the composition of a stainless steel that is used in a given application. Now what we essentially then have is we need to introduce a four-dimensional system. So such four-dimensional system, like constructing or illustrating or introducing or rather depicting such four-dimensional system is not easy. So therefore it is possible, however, it is possible for us to consider a four different vectors or a four-dimensional vector space and express it numerically. So therefore, when you consider, particularly when you consider the context of material research, a multi-dimensional vector space is hugely relevant to us because we are often dealing with composition that comprises of more than three alloying elements, more than two alloying elements. When you move away from the ternary system, it becomes, or when you move away from ternary system, it becomes, or move away from system, the quaternary system, wherein we have three independent alloying elements. When you move away from this quaternary system, what essentially then we would need is, we would need not a graphical representation, but rather a numerical representation, a vectorial representation of our concentration. And this is possible when we have a multidimensional representation. So what essentially we are doing is, particularly when we are doing data analysis, wherein we are approximating, we are relating the composition which has several different alloying elements. So which has carbon, manganese, chromium, molybdenum, and so on and so forth. And when we want to relate all this to a given property, this is only possible when we have a multidimensional vector space. When we have a multidimensional vector space. And that's the reason why often in the data science lingual, such system or such data sets are referred to as, so they get rid of the term vectors and space, so such data set are referred to as the multidimensional data set. So what we see here is the nature of the basis allow us to relate the system on the orthonormal basis as, or treat the orthonormal basis, the space that is created by the orthonormal basis, as a vector space. And the vector space, even though when you consider graphically it is rather restricted to three-dimensional, it can be extended more than three-dimensional. So the vector space, the basis that we consider I, j, and k, it can be expanded further. Particularly when you consider it in the context of composition, we need to have additional vectors to represent the composition of a stainless steel, for example. So therefore, it is possible for us to consider beyond the three-dimensional vector space to multi-dimensional vector space. Even though it is difficult for us to rather visualize it, it is possible for us to understand the meaning of a multi-dimensional vector space. In a multi-dimensional vector space, it is possible for us to describe the composition. So numerically, what we are doing is we are describing a concentration, and this is possible only in a multidimensional vector space. And if you could recollect, one way of writing a given vector would be of this form, that is AI. So we are just considering a three-dimensional rather the vector A vector that we have considered before, this A vector that we have considered before, this it can be represented in this way: AI, AG, and AK. So this is so this vector, it lies within the three-dimensional vector space. And now when you consider a composition of this sort, a composition that comprises of more than three alloying elements, then the way we would represent it would be something like this, so on and so forth, and ultimately you have an n-dimensional vector space. So this is a conventional three-dimensional vector space and a vector that is represented in this manner. So this is a conventional representation of a vector. We write it as a column vector. We just consider these magnitude and we write it as a column vector. And when you expand these three magnitudes, and when you are the vector that you are describing as more than three magnitudes to denote it, to represent it, then what we end up having is a multidimensional vector. This is conventional representation, a conventional vector. This is a multidimensional vectors. This play a key role when we are trying to relate our composition, the composition of our material that we are interested in, our highly applicable material to its property. So in the subsequent lecture, we will also try to revisit the other operations associated with vector, and we will try to build on this understanding. Goodbye.